Good morning, students. Just after the completion of the chapter surface chemistry, next we switch over to next chapter, that is the solid state. Mark that. Next chapter is the solid state. Mark that. First we discuss the introduction part. Today is the first class. In the first class, I try to complete the introduction part. What do you mean by solid? Classification of solid as crystalline solid and amorphous solid. Distinction between crystalline solid and amorphous solid. Classification of crystalline solid basing upon the magnitude of forces of attraction, types of constituent particle present, that is ionic solid, covalent solid, molecular solid and metallic solid. Next, two term is there, that is crystal lattice or space lattice and unit cell. Next, types of unit cell is of two types, that is a simple or primitive unit cell and a centered unit cell, non-primitive unit cell. Then calculation of number of atoms present in a unit cell. Next, closed packing. Under this, that is one-dimensional closed packing, two-dimensional closed packing and three-dimensional closed packing. So before starting the chapter, I suggest you one thing, that it is the three-dimensional concept. But we go through this one through the whiteboard, it is a two-dimension. So sometimes it is created some confusion. I repeat again. The solid state, the concept is three-dimension, but I try to clarify on this board which is a two-dimension. Sometimes it creates some confusion. So let us start first one, that means the introduction part. What do you mean by solid? We know already, that is basing upon the magnitude of forces of attraction of the constituent particles, the matter, classified into three states, that is solid state, liquid state and gaseous state. Solid state is one of the states where the magnitude of forces of attraction is maximum and they possess definite shape and definite volume. Next we discuss, that is classification of solid. Next is classification of solid. Depending upon the arrangement of the constituent particles, particles may be atoms, ions or molecules. Depending upon the arrangement, solids generally classified into two types. One is crystalline solid and one is amorphous solid. Mark that. Point 1, crystalline solid. Point 2, amorphous solid. Let us discuss one by one. What do you mean by crystalline solid? A solid is said to be crystalline. A solid is said to be crystalline if the constituent particles, that is atoms, ions or molecules, are arranged in orderly manner, in regular orderly manner in three dimensions for a long range, for a long time period in comparison to the internuclear distance. I repeat again. A solid is said to be crystalline if the constituent particles, that is atom, ion or molecules, arranged in a regular orderly manner in three-dimensional space for a long distances in comparison to internuclear distance. For example, sodium chloride, potassium chloride, ammonium chloride. These are some examples of crystalline solid. Next we discuss the amorphous solid. A solid is said to be amorphous. A solid is said to be amorphous if there is no regular orderly arrangement of the constituent particle. The orderly arrangement of the constituent particle is very short range order. Then it is known as amorphous solid. For example, fused silica, rubber, plastic, these are common examples of amorphous solid. Next we discuss what is the difference between crystalline solid and amorphous solid. Next we discuss difference between crystalline solid and amorphous solid. Make a table. One side crystalline solid, one side amorphous solid. I remind all of you that while writing the difference, writing the distinction, always focus to first point definition. So what is the point one? Point one, the constituent particles are arranged orderly manner in three-dimensional space for a long time period. Point one, the constituent particles are not arranged orderly in three-dimensional space. Point two, they possess a definite geometry. Point two, they do not have a definite geometry. Next, they have a sharp melting point. Next, they do not have sharp melting point. Next, the most important, they are anisotropic in nature. They have isotropic in nature. Very, very important point is there. The crystalline solid are anisotropic in nature. What do you mean by anisotropic? That means their physical properties are different in different direction. While amorphous solid are isotropic, that means their physical properties same value in different direction. Next, When caught with a sharp knife, in case of crystalline solid, when caught with a sharp knife, they produce a sharp image, a sharp cut, while when caught with a sharp knife, produce a rough surface. Next, crystalline solids are not compressible, while amorphous solid may be compressible. Next, crystalline solid are known as true solid, while amorphous solid are known as pseudo solid, false solid, or supercooled liquid. These are the difference between crystalline solid and amorphous solid. Very, very important 2-mark question for this chapter. Distinguish between crystalline solid and amorphous solid. Next, we'll go through the classification of crystalline solid. Next, we'll discuss classification of crystalline solid. Again, crystalline solids are classified into different types depending upon the nature of the constituent particles and also the magnitude of forces of attraction. I repeat again, depending upon the nature of the constituent particles and the types of force binding the constituent particle together, crystalline solids are classified as point 1, ionic solid, point 2, covalent solid, point 3, molecular solid, point 4, metallic solid. Crystalline solid are classified into 4 types. One is known as ionic solid, one is known as covalent solid, one is known as molecular solid, and last one is known as metallic solid, depending upon the constituent particle and the magnitude of type of force. Mark that. In case of ionic solid, the constituent particles are oppositely charged ions held together by electrostatic forces of attraction. While in case of covalent solid, the constituent particles are non-metal atoms held together by strong covalent bond. In case of molecular solid, the constituent particles are molecules. Again, depending upon the type of forces, the magnitude of forces, molecular solid again classified into 3 types. That is polar molecular solid, second one non-polar molecular solid, third one hydrogen bonded molecular solid. Mark that. In case of polar molecular solid, the constituent particles are polar molecules like NH3, CO2, CH4, the polar molecular solid like this one, which are held together by dipole-dipole interaction. While in case of non-polar molecular solid, the constituent particles are atoms like noble gases or non-polar molecules like H2, Cl2, I2, etc. And here these are held together by dispersion process. While the third one, that is hydrogen bonded molecular solid, here the constituent particles contain hydrogen atom which is attached to strong electronegative element, that is nitrogen, oxygen and chlorine. That means thereby formation of held together by strong intermolecular hydrogen bonding. While the last one is metallic solid, where the constituent particles are metal ions surrounded by mobile electrons, in which the positively charged metal ion known as kernels are held together among themselves by metallic bond. These are some classification of crystalline solid. Let us discuss one by one. First one is ionic solid. I repeat again. Ionic solid is a type of solid in which the constituent particles are oppositely charged ions and held together by strong Coulombic forces of attraction. They have high melting point, boiling point. They are hard and rigid. They are bad conductor of heat and electricity in solid state. However, they conduct heat and electricity in molten or in aqueous form. They are polar in nature. They dissolve in polar solvent and insoluble in non-polar solvent. These are some characteristics and properties of ionic solid. Sodium chloride, potassium chloride, these are some examples. Next we go to covalent solid. It is a type of solid in which the constituent particles are non-metal atoms held together by strong covalent bond forming a giant structure. For example, graphite, for example, diamond, silicon carbide, SiC. These are some examples. And they possess some characteristics, property, that is, they are hard and rigid, possess high value of MP and Vp. They are bad conductor of heat and electricity. One important thing, remember that means graphite is also comes under covalent solid, but one exception is that they are good, it is the good conductor of heat and electricity. Normally, all the covalent solid are bad conductor of heat and electricity. One exception is graphite. Next, we go to molecular solid. A solid is said to be molecular if the constituent particles are a molecule. Again, depending upon the types of force holding the corresponding molecules, molecular solid are of three types. One is known as polar molecular solid, one is known as non-polar molecular solid, one is known as hydrogen bonded molecular solid. In case of polar molecular solid, the constituent particles are polar molecules like NH3, CO2, CH4, which are held together by dipole-dipole interaction. They possess some characteristic property, that is, they are soft solid. Normally at room temperature, they are liquid or gases. That is bad conductor of heat and electricity, having low value of a melting point and a boiling point. Next, that is non-polar molecular solid. That means solid is said to be non-polar molecular solid if the constituent particles are noble gases, atoms like noble gases, or that is non-polar molecules like H2, Cl2, I2, etc., which are held together by dispersion forces. They also possess similar characteristic property of the polar molecular solid. That is, they are liquid or gases, they are soft in nature, possess low value of boiling point and melting point. Normally, if we compare the melting point, then polar molecular solid possess somewhat higher value of melting point, boiling point in comparison to non-polar molecular solid. Next one is hydrogen bonded molecular solid. A solid is said to be hydrogen bonded molecular solid if the constituent particles possess hydrogen, which is attached to highly electronegative element, that is nitrogen, oxygen and a fluorine, held together by strong intermolecular hydrogen bonding. They are normally soft solid. They possess high value of APUP and all other properties similar to polar molecular solid. Next we discuss, that is metallic solid. A solid is said to be metallic solid if the constituent particles are positively charged metal ion known as kernel, which are surrounded by negatively charged electron density, electron cloud. And here, each metal atom, positively charged metal ion, is bonded by a bond known as a metallic bond. All metals and alloy comes under this solid. They also possess some characteristics. That is, they are hard, possess malleability and ductility, good conductor of heat and electricity. They exhibit the lustrous nature. These are some characteristic property of metallic solid. So it is all about the classification of crystalline solid. Next we discuss two terms. One is known as crystal lattice and one is known as unit cell. So next we discuss two terms. One is known as crystal lattice or space lattice and one is known as unit cell. So first we discuss crystal lattice or it is known as space lattice. What do you mean by crystal lattice or space lattice? That means in crystalline solid, you have to observe that the small three-dimensional portion when repeat for a long time in different directions, x-axis, y-axis, z-axis, for a long time period to form a single giant unit. Then the single giant unit is known as crystal lattice and the small repeating unit which repeat itself for a long time period is known as unit cell. Mark there two terms is there. One is crystal lattice and one is known as unit cell. I repeat again. When a small, simple, repeating unit repeat itself in different axes, x-axis, y-axis and z-axis for a long time period to form a single giant unit, then the single giant unit is known as a crystal lattice, while the small, simple, repeating unit is known as unit cell. In order to understand this one, let us compare this concept with the wall. Mark that this wall is made up of bricks. Large number of small similar bricks when arranged themselves for a long time period to form a big wall. So this big wall is treated as the crystal lattice, while the small piece of bricks is known as the unit cell. Next we discuss the different types of unit cell. Next, we discuss different types of unit cell. Unit cell are of two types. Unit cell are of two types depending upon the arrangement. One is known as simple or primitive unit cell, and one is known as centered or non-primitive unit cell. Let us discuss one by one. First one is simple unit cell. What do you mean by simple unit cell? Mark that. Let us observe the diagram. It is a case of unit cell. It is one picture of unit cell. Mark that. In unit cell, 1, 2, 3, 4, 5, 6, 7, 8. 8 corners are there, and in 8 corners, one atoms is there. Mark that. Look after this. This one is taken as a simple unit cell. 1, 2, 3, 4, 5, 6, 7, 8. 8 corners are there. If each corner occupied by a single atom, then it is known as simple or primitive unit cell. Next is centered or non-primitive unit cell. That means, in addition to the 8 corner, in addition 1, 2, 3, 4, 5, 6, 7, 8, in addition to the 8 corner, again, there are some other atoms possessing different places. Depending upon that one, the non-primitive unit cell again classified into 3 types. Centered or non-primitive unit cell again classified into 3 types. That means body, centered, cubic unit cell, that is BCC. Next, face, centered, cubic, that is FCC. And another one is end, centered, cubic. Mark that. I repeat again. The non-primitive unit cell or centered unit cell is of 3 types. In addition to the 8 corner, again, other places occupied by the atoms, depending upon that one, is 3 types. One is body centered cubic, BCC. One is FCC, face centered cubic, and one is end centered cubic. Let us discuss one by one. Mark that. I draw again. One, 2, 3, 4, 5, 6, 7, 8. In addition to 8 corner, then another one point is there at the body. Another one atom present as the, if it is total as the taken as a body, then center of another one atom is there. That is known as body centered cubic or BCC. Next one is face centered cubic. Mark that. How many faces are there? 6 faces. It is 1, it is 2, 3, 4, 5, 6. 6 faces is there. So in addition to the 8 corner, if another one atom is there at the center of each face, mark that. That means It is one atom, center of this space, 2, that is 3, 4, it is 5, this one the 5 and this one the 6. Mark that. In addition to the 8 corner, if another one atoms are each present at the center of each face, then it is known as face centered cubic. Last one is end centered cubic. That means in addition to the 8 corner, if we mark that in one plane, 2 faces is there, 2 atom is there at the 2 opposite faces in one axis, then it is known as end centered cubic. So unit cell are of 2 types. One is simple or primitive, one is centered or non-primitive. Again, non-primitive is of 3 types. One is BCC, body centered cubic. Next, FCC, face centered cubic. Last one is end centered cubic. Next, we discuss the total number of atoms present in a unit cell. Next, calculation of total number of atoms present in a unit cell. For this, we have to select 3 different types. One is a simple cubic, one is a body centered cubic, one is a face centered cubic. First one discuss simple cubic crystal. Mark that. For a simple cubic, look at it is a simple cubic. How many corners? 1, 2, 3, 4, 5, 6, 7, 8. 8 corners are there. In 8 corners, one atom is there. Then, if we select one atom, what is its contribution towards the total? That is 1 by 8. I repeat again. Mark that. It is a simple. Let us assume that it is a simple cubic. 8 where 8 corners are occupied by 8 atoms. Then, what is the contribution of one atom for the total? That is 1 by 8. Hence, the total contribution of one atom in a simple cubic is equal to 8 into 1 by 8 is equal to 1. This is for simple cubic. Next is point 2 for BCC, body centered cubic crystal. What is a BCC arrangement? Mark that. In addition to the 8 corner, another one atom is there as a center of a body. So, first thing is there. So, total contribution, bit 1, total contribution of one atom in a simple cubic is equal to 8 into 1 by 8 is equal to 1, and the number of atoms in a body is equal to 1. Therefore, the total number of atoms in a unit cell is equal to 1 plus 1, that is 2. Hence, in case of simple cubic, total number of atoms, that is 1. In case of BCC, total number of atoms is 2. Next is for face centered cubic, FCC. Face centered cubic means, mark that, in case of face centered cubic, what is FCC type of arrangement? 8 corner is there. In addition to 8 corner, 6 faces, 1, 2, 3, 4, six faces is there, and one atom is there at the center of each face. So mark that. It is one cubic system. Here 8 atom is there. Here also 8 atom in the corner. If we look after the face, one is there at the center of this face. One is there at the center of face. So what is the contribution of one atom for these two? That is 1 by 2. One atom in this space, one atom in this space. When we join this one, what is the contribution of one atom for this space? 1 by 2. So how many faces are there? 6 faces. So what is the total contribution? That means that is 6 into 1 by 2. Hence, third one, for FCC crystal system, bit 1, that means for simple cubic, that is at the corner, total contribution is equal to 8 into 1 by 8 is equal to 1, and point 2, for 6 faces, for 6 faces, the total contribution is equal to 1 by 2 into 6, that is 3. Therefore, total number of atoms present in FCC type of system is equal to 1 plus 3 is equal to 4. That means, in case of simple cubic unit cell, total number of atoms present is 1. In case of BCC, that is 2. And in case of FCC, that is 4. Let us apply this concept in solving one problem. One question is there. A compound is formed by taking two different elements A and B, forms a cubic crystal in which A atoms are present at the corners while B atoms are present at the faces. Derive the formula of the compound. Mark the question. Two type of atoms are there, that is atom A and atom B, form a cubic structure. According to question, atoms A are present at the corner. 8 corner is there. 8 atoms are there. For each atom, what is the contribution? That is 8 into 1 by 8. That is answer. For contribution at the corner is equal to 8 into 1 by 8 is equal to 1, and also for faces the contribution, that is 1 by 2 into 6, that is 3. So that is the ratio between atoms A and B. Ratio between atoms A and B is equal to 1:3. Indicate that The formula of the compound is AB3. It is a 2-mark question. Whether the crystal system it may be given in the question simple cubic or BCC or FCC. The number of atoms present at the corner or may be present at the body center or may be present at the face center. Next, we discuss the packing of crystal, packing of unit cell in a crystal. Next, we discuss close packing in a crystal. What do you mean by packing and close packing? The orderly arrangement of the constituent particles known as packing. And this packing is going on in such a way that the constituent particles, if arranged in such a way that constituent particles occupy maximum space, leave a minimum space as vacant space, then that type of packing is known as closed packing. I repeat again, a packing is said to be closed packing if the constituent particles are orderly arranged in such a way that it occupies the maximum space. And before going to this concept, it is to be assumed that the constituent particles are spherical in nature with uniform size. So there are 3 types of closed packing, that is one-dimensional closed packing. Next, 2-dimensional closed packing. Next, 3-dimensional closed packing. Let us discuss one by one. First one is one-dimensional closed packing. Mark that. What do we mean by one-dimensional closed packing? Before going to this, I repeat again. We have to assume that the constituent particles are spherical nature having equal size. So, there is only one way is there to arrange the constituent particle in one dimension. That is, mark that, it is one plane. It is known as one-dimensional closed packing. So in this arrangement, we observe that every system, every sphere came in contact with the nearest 2 sphere. So one term is there that is known as the coordination number C dot n. It is defined as the number of nearest neighbor. So in case of one-dimensional closed packing, it is observed that each sphere is in contact with 2 neighbor spheres. So in case of one-dimensional closed packing, C dot n is 2. Next, switch over to 2-dimensional closed packing. Next, we discuss two-dimensional closed packing. That means here the arrangement is going on the basis of rows and a column. Two-dimensional closed packing is going on if the constituent particles are arranged in horizontal rows and in vertical column. There are two type of arrangement is there. Mark that. It is one type of arrangement where the constituent particles, the spheres, are arranged in horizontally and also vertically, such that each sphere, mark that, each sphere came in contact with the four other sphere. So if we join the center, of the four sphere, then a square is formed. So this type of packing is known as square close packing. Mark that. I repeat again. That means in this type of arrangement, the spheres are arranged in horizontally as well as vertically in one alignment such that every sphere came in contact with a neighboring four sphere such that here if we draw the center of the four sphere which is came in contact with the central sphere, then a square is formed. That's why it is known as square close packing. So in this case, the coordination number is 4. Another case is there, mark that. Mark that. Here also this arrangement is horizontally and vertically. But what we observe, that means in the second row that is present in the depression, that means if it is known as the first row, if it is the second, it is the third, it is the fourth, it is the fifth, mark that. The second one is present at the depression of the first one. The third one is present in the depression of the second, and this one arrangement is going on in such a way that if we observe any sphere that is known as central sphere joined to 6 other sphere. So if we join the center of 6 other sphere, mark that. A hexagon is formed. That's why it is known as hexagonal close packing. It is known as HCP, hexagonal close packing. It is known as SCP, square close packing. And in these two arrangements, it is observed that this one is a better arrangement. Hexagonal close packing is a better arrangement because of it occupy maximum space, leave minimum space as vacant space. And as 6 other spheres join to the central sphere, so in case of hexagonal close packing, C dot n is 6, while in case of square close packing, C dot n is 4. It is all about the close packing in one dimension, close packing in 2 dimensions. Next switch over to close packing in 3 dimensions. In case of close packing in 3 dimensions, there are 2 possibilities there. One is known as hexagonal close packing and one is known as cubic close packing.